All right, so this is lesson 13. It's on substitution. I'm going to teach lesson 13 with lesson 15, and then we will come back to 14 because 13 and 15 go together. So lesson 13 is on substitution. So you're going to have two equations, first degree equations. They're going to be linear. They are going to look like 2x plus y equals 3, and maybe 3x minus 2y equals 5. You're going to have two equations. You're going to solve for one of the variables in one of them and plug that into the other equation to solve for that variable. Okay, I want to talk about linear equations. Linear equations, they're first degree. First degree equations because the degree of this term is 1, the degree of that term is 1. Every first degree equation has only one direction. It will absolutely cross the y-axis one time. Most of them only cross the axis one time, y-axis one time. And it will cross the x-axis once. Thus, it's a first degree equation. All right? So, we are going to find the point, literally, come on in, where these two equations, or these two lines, if I graph them, their point of intersection. All right, we're going to find, that's what we're doing when we're solving using substitution. We're literally finding where those two equations intersect. All right, so if you look at Sarah 6, so I'm videoing.
Okay, I was like, what's happening?
Yeah, exactly. You just got videoed. All right, so if you look at example 1 on page 72, we have x equals y plus 5, and we have 3x plus 2y equals 5. 3x plus 2y equals 5. So this first equation, and you're going to use substitution from here on out. Like in all of your maths, higher level maths, you will use substitution. It will feel different, it will be harder, but you will still use substitution. So as my boys have gotten higher in their maths, it's harder to remember the simple things like substitution. All right, so this is x equals this value, y plus 5. So in the second equation, where x is, I'm going to substitute y plus 5. So we have 3, and in for x, I'm substituting y plus 5, plus 2y equals 5. And I'm going to distribute, add like terms, move my constants to the other side, and we will solve for y. So distributing the 3, we have 3y plus 15 plus 2y equals 5. I'm going to subtract 15 from both sides, combine my like terms, and that's 5y equals negative 10, dividing by 5 on both sides, y is negative 2. That's my y value, where these two lines intersect. I'm not done. I need to solve for x. So I'm going to go back to this equation, and I'm going to again use substitution and substitute in negative 2 for y. So x equals negative 2 plus 5, and that's 3. So my solution is 3, negative 2. That is the coordinate point where those two lines intersect. All right, now not all of the equations are nice and neat, and it's x equals or y equals. Some of them are written in a different form, and you have to decide which one do I want to solve for to then substitute it in. So look at example 2 on page 72. We have 3x minus y equals 11. 3x minus y is 11. And the second equation, 2x plus 3y, 2x plus 3y equals negative 11. When you're using substitution, I'm going to look for the one variable that has a coefficient of 1. All right, but this is negative. I want it positive. Do you need a pencil?
No, I got one.
Okay. So I'm going to move the y to the right through addition. So I'm going to add the y, and I'm left with 3x equals y plus 11. Then I'm going to subtract the 11 on both sides so that I have y equals 3x minus 11. Now I have a value that is equivalent to y. And I'm going to substitute it in the other equation where y is. Why do I do this? Because I can't solve it with two variables. When I use substitution, the end result is I have only one variable, and then I can solve it. All right, so using substitution, substituting in for y, 3x minus 11 equals negative 11. Watch your negatives and positives. I distribute the 3 to both of the terms inside the parentheses. I plus 9x minus 33 equals negative 11. I'm going to add 33 on both sides. Combine my like terms. This is 22. This is 11x. I divide by 11. X is equal to 2. That's one of my solutions, but I need y. So I use substitution again. I'm always going back to this equation, the one that I solved for, to substitute in. All right, so when I substitute back in 2 for x, it's 3 times 2 minus 11 is what y equals. That's 6 minus 11, so y is negative 5. So my coordinate point is x goes first, y goes second. That's literally the point where those two lines intersect. It's a point of concurrency, if you remember that from geometry, the point where they are concurrent. All right, so this one I first had to solve for y. All right, look at the third example. For the third example, on page 79, we have x plus y is equal to 20. X plus y equals 20. And 5x plus 10y equals 150. 5x plus 10y equals 150. So in this first equation, I can solve for x or y. It doesn't matter. Which one you want to solve for?
X.
You want to solve for x. So we will subtract y on both sides. We end up with x is 20 minus y. So this is what I'm substituting in the other equation for x. So I have 5. I need to throw this one away, huh? Okay, far away.
What?
Yeah, that's on video. Oh well. 5 times, because you know, I put it on the table the other day. It got back here. I should have thrown it towards the garbage can. I actually could have maybe made it. 20 minus y plus 10y is 150. I distribute that 5. 5 times 20, that's 100, right? Minus 5y plus 10y equals 150. I'm going to subtract 100 on both sides. Combine my like terms. Negative 5 and 10 is positive 5y equals 50. And when I divide by 5 on both sides, y is 10. Not done. Got to substitute that back into this equation and solve for y. So x equals 20 minus 10. X also equals 10. So my coordinate point where these two lines intersect one another is 10, 10. Does that make sense? Does substitution make sense? There's one more piece to this lesson, and we're going to go on over that. And it's a reminder of some geometry. All right, so you have an isosceles triangle. And you're only given the lengths of the sides. So we have an isosceles, and you're only given the lengths of the sides, and they want you to find the area. 100% of the time, when you have an isosceles triangle, if I draw from a line from the vertex perpendicular to the opposite side, to the side that's not equivalent to the other two, it divides this in half. It literally bisects that side, such that this side is 2 and that side is 2. Because I can't just use the sides to calculate the area. I need the height. What's the formula for the area of a triangle? It's 1/2
Pi r squared. No, no.
base
Huh?
times height. So I know the base is 4, right? I know that the base is 4. I just don't know the height or altitude. But now I can calculate it using the Pythagorean theorem, right? So we'll label this h. So 2 squared plus h squared is going to be 5 squared. Make sense so far? So we have 4 plus h squared is 25. I'll subtract 4 from both sides. We have h squared is 21. I don't want to know what h squared is. I want to know what h is, so I take the square root of both sides. Normally when we do this in a math problem, it's plus and minus, but not so when it's the length of something. It's only the positive length. So h is the square root of 21. 21 is 3 times 7. That's in its most simplified form. So then I plug that in for my height. Square root 21. What's half times 4?
2.
So that's 2 square root of 21 is the area of the triangle. Make sense?